Here is the third part of this lecture. In this lecture, we shall discuss about thin film solar cells apart from amorphous and microcrystalline silicon solar cells, which we have already discussed in the previous part of this lecture. We shall also discuss about the multi-junction solar cells. Solar cell or photovoltaic cell is the heart of the solar renewable energy, by which we can harvest clean energy for general and commercial use. The operation of a photovoltaic cell requires the following basic attributes: the absorption of light generating either electron-hole pairs or excitons. Light is composed of different wavelengths. Only photons have more energy, which is required to generate electron-hole pair can produce excitons. The next attribute which is required is the separation of charge carriers of opposite types and extraction of those carriers to an external circuit. In this picture, we can see the wavelength of 700 nanometer cannot eject electrons from the surface of the material. The wavelength of 500 nanometers can eject electrons, and the wavelength of 400 nanometers can eject electrons as well as provide kinetic energy for the electrons to move on. A photovoltaic cell works on the principle of photoelectric effect. It consists of a p-n junction created by photoelectric effect. The electrons are transferred through an external circuit and utilized in applications. The materials chosen for such applications have lowest band gaps between the conduction band and the valence band so that the electrons can be easily ejected off from the valence band and transferred to the conduction band, leaving behind a hole. This separation of electron and the hole creates a voltage and electric current. Such materials are called semiconductors, or in other words, semiconductor materials, which serves the purpose nicely. The p-n junction directly converts sunlight into electricity. This electricity can be stored for later used on demand. The electrons can jump between the bands, that is, valence band and the conduction band. Incident light with energy greater than the band gap energy can be used to excite these electrons. A positive hole is left in the electron's place. This separation of electrons and holes creates a voltage and the current, as seen in the picture. There are mainly three different types of thin film solar cells, depending upon the type of semiconductor material employed, namely amorphous silicon thin film solar cells, cadmium telluride thin film solar cells, and copper indium gallium selenide thin film solar cells. The main feature of thin film technology is to look for properties and better efficiencies at lesser material bulk, where the silicon wafer-based solar cells work with wafers of typically 350 micron thickness. The thin film technology is working at 1 micron thickness, which is 1 millionth of a meter. We have already discussed about the amorphous silicon in the previous part of this lecture. The main advantage of the amorphous silicon solar cells is that it provides cheaper alternative to the wafer silicon solar cells, which is sometimes not easy to find and demand exceeds supply. Also, it's ideal to run small scale applications. However, the disadvantage is that the thin layers of amorphous silicon absorb sunlight less efficiently, hence generate less efficiency. Therefore, not suitable for large-scale applications such as solar-powered buildings, etc. To address this problem and overcome the limitations of silicon-based solar cells, cadmium telluride and copper indium gallium selenide thin film solar cells are being tested. In a typical CIGS cell on a glass substrate, a layer of molybdenum has to be deposited to make an electrode. If a metal foil is used as a substrate instead of glass, this extra layer of molybdenum is not required, as the metal foil itself acts as an electrode. The other layer of zinc oxide is deposited to create another electrode, and in between the two layers is sandwiched the semiconductor material and cadmium sulfide, which acts as N-type and P-type materials respectively, as the source material to create electrons and electric current. The deposition of CIGS films into a substrate is frequently done in a vacuum by evaporative or sputtering methods. Copper, gallium, indium are deposited first and then annealed with a selenide vapor to give rise the final CIGS structure. The deposition of the materials can also be done without a vacuum using bath deposition or spin coating of nanoparticles or electroplating. However, these techniques are still under research. In the recent years, printing techniques are being developed. CIGS deposited onto a flexible surface allow its versatile usage over curved surface and free from risk of shattering. Here is a schematic representation and some models of CIGS solar cell modules. The first picture is the CIGS cell deposited over a glass substrate. For this, a back contact molybdenum layer is required. On the top of this absorber layer CIGS, which is p-doped, and on the top of this layer buffer layer and ZNO, both n-doped, is deposited. On the top, the window TCO ZNO aluminum layer is deposited for the another contact. The rest two pictures are the CIGS solar cells deposited on flexible substrate. The cadmium telluride solar cell has a similar sandwich structure as the CIGS solar cell structure. In the cadmium telluride solar cell, one electrode is made from a layer of carbon paste infused with copper, another layer from tin oxide or cadmium stannate, that is CD2SNO4. The semiconductor in this structure is cadmium telluride. This cadmium telluride along with cadmium sulfide creates the N-type and P-type layers required to form a p-n junction for the PV cell to function. The theoretical maximum for the silicon wafer solar cells is approximately 50%. However, in practical applications, it reaches up to 15 to 25% only. On the contrary, the thin film alternatives such as cadmium telluride solar cells has reached just more than 15 to 20%, as well as CIGS solar cells have reached approximately 20% efficiency. Another main advantage of cadmium telluride solar cells over the silicon wafer solar cells is the manufacturing cost, as cadmium is abundant and generated as a byproduct of important industrial materials like zinc, and cadmium telluride panels are capable of absorbing sunlight close to the ideal wavelength or energy at shorter wavelengths than the traditional silicon panels can. But the serious drawback of cadmium telluride solar cell panels is the toxicity of cadmium. Like mercury, it can enter and accumulate in the food chain and affect the health of the body. Furthermore, decommissioning and disposal of waste panels is a huge concern. Here is some visuals of cadmium telluride solar cells fabricated on flexible as well as rigid surfaces. Fully functional, monolithically integrated, flexible solar module consists of 6 cells is shown here. It is based on cadmium telluride. EMPA researchers recently received a new world record in energy conversion efficiency of 13.8% with this type of solar cells. Next in the list is multi-junction photovoltaic cell. Multi-junction solar cell structure consists of multiple layers of single-junction solar cells on the top of one another, and there arises a gradation of band gap of the materials from the top to the bottom going to be smaller and smaller. This arrangement with different band gaps covers a range of solar spectrum to achieve the highest efficiency conversion. Actually, more precisely, it allows to absorb and convert the photons that have energies greater than the band gap of that layer and less than the band gap of the higher layer. Such multi-junction solar cell structure requires materials with optimal band gaps which simultaneously allow high efficiency through low defect densities, and very good candidates are the alloys of group 3 and 4 of the periodic table. These include gallium arsenide, germanium, forming a two-junction structure, gallium arsenide germanium, and gallium indium diphosphide making a three-junction structure, indium gallium phosphide, gallium arsenide, indium gallium arsenic nitride, germanium making a four-junction structure, and in the picture at the right hand side shows a 7-junction structure. Multiple junction solar cells are typically fabricated using metallo-organic vapor phase epitaxy and plasma-enhanced chemical vapor deposition. Gallium arsenide-based multi-junction solar cells have demonstrated to produce highest efficiencies till date. The structure of a multi-junctional solar cell are as follows. There are 6 important types of layers: PN junction, back surface field layers, window layers, tunnel junctions, and anti-reflective coating and metallic contacts. In the second picture we see the graph of spectral radiance E versus wavelength over atmospheric mass 1.5 of the solar spectrum, together with the maximum electricity conversion efficiency for every junction as a function of wavelength. A multi-junction device is a stack of individual single-junction cells in descending order of the band gap. The top cell captures the highest energy photon and passes the rest of the photons on to be absorbed by lower band gap cells. Here is listed the important steps of cell fabrication. In the first step, metallo-organic chemical vapor deposition growth of device structure on the reusable gallium arsenide substrate is done. This step is followed by deposition of back contact metals and bonding of sample to flexible handle is done. Dissolution of aluminum arsenide release layer to produce thin film device on metal and flexible backing. And finally, completion of the device fabrication is done. Generally, a modern photovoltaic cell contains multiple number of transparent layers to absorb the solar spectrum. The top layer absorbs the high energy light and passes rest through the inner layers. High energy photon captures take place in the UV visible region of the spectrum. The photon energy must be sufficient for the efficient production of photo-excited charges, that is, electrons and holes. These electrons must be efficiently transferred to an external circuit before it recombines with the hole. The semiconductor material must be stable in both ways, that is, chemically and photochemically. Furthermore, it must be cheap in cost, durable in the environment, and can be processed easily via suitable technologies. Gallium arsenide is an important semiconductor material for making multijunction solar cells, but the cost of the fabrication is high. Altogether, the efficiencies of multijunction solar cells is also as high as 29% as of a report in the year 2019. This high efficiency is attributed to both absorption of the broad wavelength range in the solar spectrum and the extremely high quality of gallium arsenide epitaxial growth, surface passivation by aluminium gallium arsenide, and the promotion of photon recycling by the thin film design. Until date, gallium arsenide indium phosphide, a 5-junction solar cell, has shown efficiency as high as 39% as reported by Spectrolab 5-junction experiment. Here is the comparison of efficiencies of the 4 main types of solar cells have been shown. The band gap of amorphous silicon is 1.7 electron volt, that of gallium arsenide is 1.45 electron volt, crystalline silicon is 1.1 electron volt, and germanium is the lowest at 0.7 electron volt. The efficiencies shown by these solar cells are: for crystalline silicon it is 26%, and the gallium arsenide shows a maximum efficiency of 29%, crystalline silicon shows a maximum efficiency of 27%, and that of germanium shows 13%. Below in this picture, a super thin layer of 30 angstroms of gallium arsenide solar cell which can function to produce electricity. The another 2 pictures are thin layered gallium arsenide solar cells fabricated for sale. The gallium arsenide heterojunction solar cells were first developed by the team led by Joris Alferov in 1970s in the former USSR. In the early 1980s, the efficiencies were improved to an extent to surpass that of conventional crystalline silicon-based solar cells. In the years since 1990s, gallium arsenide solar cells took over silicon photovoltaic arrays for satellite applications. However, the first known operational use of gallium arsenide solar cells in the space was constructed for Venera 3 mission launched in 1965 and were chosen for their higher performance in elevated temperature environments. In the later years after the 90s, dual and triple junction solar cells based on gallium arsenide with germanium and indium gallium phosphide layers were developed, which demonstrated a record efficiency of 32% and can operate with solar concentrators of light as 2000 suns. The Mars exploration rovers Spirit and Opportunity satellites meant to explore the Mars surface was powered by gallium arsenide solar cells. Also, many of the solar cars utilize gallium arsenide in the solar arrays. Here in the picture is a satellite MidStar 1 assembled with high efficiency triple junction gallium arsenide solar cells covering the sides. The second picture is Mars exploration rover Spirit and Opportunity with the solar panels made of gallium arsenide. Now we look at a case study and comparison of performance of the four main photovoltaic cells. In this endeavor, four photovoltaic cells have been used, namely monocrystalline silicon, polycrystalline silicon, amorphous silicon, and copper indium gallium diselenide. The experimental setup is displayed here in this slide. It consists of the four main photovoltaic modules: polycrystalline silicon module, monocrystalline silicon module, amorphous silicon module, and CIGS silicon module. The measurement apparatuses are solar module analyzer, solar power meter, and thermometer display. The measuring apparatus from right to left are shown here: solar module analyzer, then solar power meter, and the digital thermometer. In this slide, comparison of results is shown. As we see, the temperature is higher in the month of May. The performance is recorded high in the month of January, explaining that high temperature is not conducive to solar cell performance. The microcrystalline silicon and polycrystalline silicon constitute higher efficiencies, followed by amorphous silicon and then CIGS solar cells. Here in this slide, the temperature effect on the fill factor is shown. The fill factor, abbreviated as FF, is a parameter which characterizes the non-linear electrical behavior of the solar cell. Fill factor is defined as the ratio of maximum power from the solar cell to the product of open circuit voltage and short circuit current. Now we shall discuss about the Shockley-Queisser efficiency limit or SQ limit of photovoltaic cells. In physics, the Shockley-Queisser limit or detailed balance limit or Shockley-Queisser efficiency limit or SQ limit refers to the maximum theoretical efficiency of a solar cell using a single p-n junction to collect power from the cell. It was first calculated by William Shockley and Hans Joachim Queisser at Shockley Semiconductor in 1961. The limit is one of the most fundamental to solar energy production and is considered to be one of the most important contributions in the field. The limit places maximum solar conversion efficiency around 33.7%, assuming a single p-n junction with a band gap of 1.34 electron volt using an air mass of 1.5. For space, the air mass is taken as 0. This means of all the power contained in sunlight falling on an ideal solar cell of about 1000 watts per square meters, only 33.7% of that would ever be turned into electricity, that is 337 watt per square meters. The most popular solar cell material, silicon, has less favorable band gap of 1.1 electron volt, resulting in a maximum efficiency of about 32% theoretically. Modern commercial monocrystalline solar cells produces about 24% of the conversion efficiency, and the losses are largely due to practical concerns like reflection of the front surface and light blockage from the thin wires on its surface. The Shockley-Queisser limit only applied to cells with a single p-n junction. Solar cells with multiple layers can outperform this limit. In the extreme, with an infinite number of layers, the corresponding limit of 86.8% using concentrated sunlight can be achieved. Here is a picture of Dawn's 10 kilowatt triple junction gallium arsenide solar array at full extension is shown. This brings us to conclude the part 3 of this lecture. Now we shall continue to the part 4 of this lecture.